Good morning and welcome to Orkney International Science Festival 2022. In this Scotland's Year of Stories, my name is Eric Walker and it's my pleasure to be hosting this session online and also streamed live to the Phoenix Cinema. Our speaker today is Professor Peter Wadhams. Peter was due to be with us in person, but unfortunately he can't make it over to Orkney this year. However, he's put in an exceptional effort and is still able to present his thought-provoking talk on climate himself via our online facilities. Peter is a polar and climate researcher, formerly director of the Scott Polar Research Institute in Cambridge, and professor at the Department of Applied Mathematics and Theoretical Physics. Now working on the removal of carbon dioxide and methane from the atmosphere with the Centre for Climate Repair at Cambridge. Currently, he's visiting professor in Turin Polytechnic, Italy. Peter is the author of A Farewell to Ice, dealing with the global loss of sea ice and its climatic consequences. And he's been a regular invitee at the Science Festival since 1992. Peter's talk today describes fire on the Amazon, fire in the Arctic, heat waves in India, and drought in California. Indeed, he brings detailed accounts and impacts from varied places all around the world. Now, this talk is being streamed both online and also to a live audience here in Kirkwall. I want to encourage everyone watching to take part in this event and ask you to please enter your comments and questions in YouTube's live chat or using the app Slido. Unfortunately, there's not going to be a roving microphone available for the audience in the theatre cinema and in the cinema, so please connect to the Slido facility now. Simply point your smartphone or tablet camera at the QR code on the screen and it will take you to the Q&A area, or visit www.slido.com and enter the code 3435541. Then you can easily enter your questions and comments and I'll present those to Peter after the talk. Peter, welcome to the festival. Over to you.
Well, thank you very much. It's a wonderful thing to be here in Orkney again, unfortunately only in spirit this year because of a medical problem. But the topic that I'm going to be talking about is, it's called Reports from the Front Line. When one thinks about front lines in war, then if you think about the First World War, the front line remained stationary for 4 years. But when you think about the war on climate today, it's a constantly changing battle between, I guess, the forces of evil and the forces of good, with the forces of evil being the fossil fuel lobby and the forces of good being the rest of the human race. And the front line on that constantly moves to and fro. So let's see what's happening and what we can do about it to try and push it in one direction. And next slide, please. Okay, well, just to rehash on climate change, which certainly exists and it can't be denied. What we have as the best representation of climate change over the last million years has been the fact that we can now take tiny samples of ice sheets from which we extract minute gas samples so that we can see what the level of carbon dioxide was in the atmosphere right back to 1 million years ago. And this is this remarkable record of carbon dioxide levels over the past 1 million years. You'll see it all looks quite good until things blew up in the last few years. Normally we the Earth goes through a number of cycles, which were discovered by a scientist in Serbia called Milankovic, and the amount of radiation reaching the Earth varies very slowly through a number of cycles which have a period of about 100,000 years. And so the Earth warms slowly for 100,000 years and then cools slowly. This is due to various fluctuations in the Earth's orbit. One is called the Chandler wobble. It's the Earth sort of wobbles like a top that's slowly running down. And there's a couple of others related to how the Earth's orbit changes. So these give you over 100,000 years, a warming and then a cooling. And so these are called glacial cycles. And when it's cooler, you have ice sheets forming on the planet. When it's warmer, they go away. So we look at the record of, and we start at the right, which is today. We can see that we had an ice age about 100,000 years ago, where the temperature went right down, or the carbon dioxide content went right down. The two are interchangeable, really. It's carbon dioxide content that determines the temperature of the atmosphere. So we went through an ice age. We started to come out of it, in fact, we came right out of it about 10 to 12,000 years ago. And every other ice age there's been in the last million years, there's been a cycle between strictly defined limits. And no one knows why the planet Earth decided to define those limits, but it did. And it said, when I'm in a warm period, I'm going to have about 280 parts per million of carbon dioxide in my atmosphere. And when it's really cold and ice age is there, it's only going to be 180. So as if it knew what it was doing, the planet decided to go between 180 and 280, and those were the limits of carbon dioxide content, until we came to the latest one, where we went up to 280, and as you can see, we didn't stop. We kept going, and we're now up to more than 400. And this is the source of all our problems, that we've got too much carbon dioxide in the atmosphere, and that is bringing us on to higher temperatures than we're comfortable with, and perhaps higher temperatures than we can survive. Next slide, please. Now, nobody knew why this was happening. We started, of course, burning fossil fuels in the 19th century, coal initially, and then oil. And the temperature started to rise, but nobody knew why, or nobody knew what was going on, until a Swedish scientist really came up with a solution. That's Svante Arrhenius in 1896 with this kind of classic paper. Interestingly, Svante Arrhenius was the great uncle of Greta Thunberg. Next slide, please. So Svante Arrhenius showed us what we're doing, and the reason he could do that was because just a few years earlier, physics had developed the gas laws, that's the Stefan Boltzmann law and other laws, which explained the differences between temperature and pressure in the atmosphere. And the gas laws could explain what happened and why it was happening. So next slide, please. This is really what was happening. If you look at the set of curves, one of the top one there is the top of the atmosphere in the Mediterranean, seen by a satellite. And we can see that as the frequency changes of radiation, different amounts of the radiation that the Earth is trying to emit are actually getting to outer space, and a lot of a lot of what we're emitting doesn't get out of the planet. So if we follow this, following this curve here, then down in these low frequencies, low wavelengths, we've got absorption of water vapor going on in the atmosphere. Then we have absorption of methane and nitrous oxide. Then there's what's called a window, which means that the planetary atmosphere is actually able to give out all of the energy that it wants to give out, goes into outer space and helps to balance the radiation we're getting from the sun. So that's called a window. But that window doesn't last long, because you then have an ozone gap or ozone hole where ozone is absorbed without being able to escape from the atmosphere, then another window. But the biggest hole of all, and that's the one which is the cause of all our problems, is the carbon dioxide window, carbon dioxide hole, where all of the radiation that should be emitted by the planet between these two frequencies is instead held back by being absorbed by the atmosphere, because this is the role that carbon dioxide plays. Then we have we go back to water vapor again. So this carbon dioxide, the more carbon dioxide you add to the atmosphere, the bigger this hole gets. So as the planet tries to emit radiation, it's being prevented by the fact that these other elements are in the atmosphere: methane, ozone, nitrous oxide, but most of all carbon dioxide. So these are called greenhouse gases, because it's the greenhouse effect, as with the greenhouse, that we're trying to emit radiation, but it's held back, and it's not by the glass of the greenhouse, but by the gases of the atmosphere. And so the Earth doesn't warm up as much as it should. Next slide. Well, that was what goes on, and we knew what was going on by 1896. But for some reason, we didn't bother to do any measurements as to how much warming was actually going on, how much carbon dioxide was accumulating in the atmosphere. And it wasn't until 1958 that anybody started to make measurements. And this was the Scripps Institution of Oceanography. And they set up an observatory on the top of Mauna Loa, which is a volcano in Hawaii, and made regular measurements, daily measurements of carbon dioxide and temperature and many other things from that day on to this. So it's absolutely vital what they've done. And these are some results. And this I call this the sort of curve of guilt, because what this shows is that the carbon dioxide level in the atmosphere has been rising and accelerating, and we've done nothing about it, basically. The level, little wiggles are seasonal changes, but the main change has been a steadily accelerating level of carbon dioxide, which has gone now way beyond 400 parts per million. Although when they started in 1958, it was only 310, which wasn't far above the level at the end of the last ice age. So we hadn't played around with the atmosphere that much before the 1950s, but then we certainly started doing that. Next slide, please. The carbon dioxide content of the atmosphere holds back heat that the Earth is trying to emit. So there's a real balance between the amount of carbon dioxide in the atmosphere and global temperatures. The two run together. So this is what global temperatures have done in the last 100 years or so. And we can see that, again, global temperatures have risen in an accelerating way. And they're now, according to this curve, they're 1.6 degrees above what they were before the Industrial Revolution. And this is a very important result, because when you look at what people tell you about global warming, they keep saying it's 1.2 degrees. And if we're careful, we can avoid 1.5 degrees. 1.5 degrees of warming is generally reckoned to be disastrous for the planet, for people, for ecosystems. So the Intergovernmental Panel on Climate Change, which is the governing body for research in this area, tells us that we've only had 1.2 degrees so far. So if we really work hard, we can maybe avoid 1.5. But what's curious to a scientist is when you look at this graph, you see it has already exceeded 1.5. The reason for the discrepancy is that the Intergovernmental Panel on Climate Change cheats by starting at some point in the 20th century, about 1940, instead of starting when we had the Industrial Revolution in the end of the 18th century. So by moving the goalposts literally, they're making it look as if we haven't had as much warming as we actually have. So in fact, we have already exceeded our 1.5 degree limit. Next slide, please. We can see this in various ways. This is a ranking curve. And in fact, my wife has a knitting pattern based on this, which is called for a kind of ecological scarf. And what it is you take each month of the year and you look at what was the hottest month in the last 40 years. So let's look at, say, March. We look at all the Marches, and the numbers here show which is the hottest and which is the coolest. So here we have the hottest March was in 2015. The next hottest was in 2013, and then the next one was in 2016. All the hottest Marches were over the past few years. When you go back to the 1970s and 1980s, you find the numbers, the ranking is going up, which means it was cooler. So the blue shows cooler months and the red shows warmer months. And for every month of the year, the warmest ones have been the past few years, and the coolest ones have been back in 30 or 40 years ago. There's no doubt that it doesn't matter what month of the year you look at, it's getting warmer. Next slide, please. Now, if we look at the records, well, they're still being written because they're all being confirmed, so that the record data we've got dates from 2021, but several records were both broken. The hottest day ever recorded was in the United Arab Emirates, and that was 51.8 degrees, a place called Swaihan. And that will probably be beaten because there's been hotter days in India this year, and they're just being confirmed. Next slide, please. But the weird thing is, and that's increasingly weird, is intense heat in places where you don't expect it. And one of those is a town in the Rockies called Lytton in British Columbia, where it's quite cold. I mean, you see snow and ice around there in the winter. It's high up. It's a place where you don't expect any particular warming to happen, but miraculously, or it suddenly warmed up in 2021 to 47.9 degrees, and that was so hot, and it was so dry that the town just caught fire. It was a town in the forests, the forest caught fire and the town was burnt to the ground. So there's no Lytton anymore. And people were just amazed, how could a town in a cold region of Canada just catch fire because of a heat wave? But it did. Next slide, please. And if we look at the average temperature of the world, we find that the 6 hottest years are the last 6. There's no doubt that we're warming up rapidly. So you look back 20, 30, 40 years, the temperature is definitely much lower, and heat records are being broken every year. Next slide. So here's some more assorted evidence of rapid warming going on, that India and Pakistan have been showing these enormous high temperatures, which have reached the point where it's very nearly at the point where you drop dead if you're in the street in Jacobabad. If you have a combination of very high temperature and a high wet bulb temperature, which means humidity, then it's calculated at 35 degrees. Combination of those two would kill you, and it got up to 33.1 in India. In other words, people were very close to just dropping dead in the street. We've had over half of all the greenhouse gas emissions that we've done. You'd think, having discovered what we were doing in 1896, we might have made some effort to reduce emissions, but we haven't. And over half of the total emissions since the Industrial Revolution have been done in the last 30 years. And the wildfires, for instance, are a symbol of, again, uncontrolled heating. And wildfires in California covered 4.3 million acres last year, and normally it's less than 1 million. And then you have extraordinary phenomena which haven't been seen before, called heat rivers or heat domes, which cause intense heating over a small area. And this was the thing that wiped out Lytton, BC. Next slide, please. Then it's not confined to warmer areas, but you find these extreme heat events in the Antarctic. So the red peak here on the left-hand side was recorded on the top of the Antarctic ice sheet. That was Dome C, where they're drilling a hole through the ice sheet to look at temperature and look at carbon dioxide. But while drilling from a height of 9,000 feet above sea level, suddenly the temperature went up, and it went up by 38 degrees above the normal temperature. So instead of intense cold, you had quite a warm day on top of your Antarctic ice sheet. So that's the red peak that we have here. Never seen before or since. Then, okay, there we go. Modelers who are modeling climate change tell us, to our concern, that there's going to be, or just coming up, an acceleration of the global warming rate. Again, because of the carbon dioxide emissions going up and the physics of the atmosphere, they expect that the global warming rate will increase this year from the blue curve, which is rising at quite a high rate, but to the red curve, where the rate of warming is double. So we can expect this year to see the warming rate of the atmosphere double if the models are correct, which is pretty frightening. Next slide. Also, the ice in the Arctic is disappearing. This ice is one of the things I study. And this is the actual record now, not modelling. This is what's gone on. And we can see that the blue curve shows that the ice area has been decreasing steadily over the years, but the red shows the decrease during the summer months, September, which is the time of greatest retreat, and we can see that that extreme, when extrapolated with a model, brings us to zero very soon, or at some stage within the next decade. All of the sea ice will disappear in the summer. Next slide. Well, anyway, this was what it used to be like when I was young and was starting to work on the Arctic. It didn't seem to be doing this in such a crazy way. So this was what one might call the stable Arctic, and it consisted of the light blue was ice. So the whole of the Arctic Ocean was covered with ice in the winter, as well as Baffin Bay, Hudson Bay, Sea of Okhotsk. It was the Arctic plus a lot of surrounding seas were ice covered in winter. The red, by the way, is fast ice. That's ice that's fixed to the shore, and I'll show you a picture of that. Then in summer, the ice retreated, but it didn't retreat that far. It was still nearly all the way up to the coastlines of Siberia and North America. So you couldn't really easily sail through the Northwest Passage, as I talked about in a previous talk. And it really still kind of glued together Siberia and North America, so that it really looked like a single continent, single landmass. Next slide. But that didn't stay the way things were. The ice started to retreat, especially in summer. And here we see how far it went. The black is the summer ice limits as they used to be. The yellow was in 2007, which was a record. And the white is 2012, which is the record so far. So the summer ice is clearly retreating. Next slide. The little red areas I showed, which are fast ice in summer, that's in winter rather. This was when the ice would just freeze up against the coast, and it would be a flat, solid ice surface. So in the old days, this was 2012. You could Inuit hunters could use that ice for sledging, for polar bear hunting. So here we are on a polar bear hunt with a couple of very strong wooden sledges and an iceberg in the background. This is the northwestern coast of Greenland, a place called Karnak. And so this was how Inuit hunters would work. But next slide. Here is what it's like now. This is exactly the same scene as the one I showed, the last one I showed. In fact, it's taken from the same spot and taken from the same sledge. And the dog team now, instead of galloping across this frozen mass of ice, has to wade through water. There's a layer of meltwater on top of the ice, making it very dangerous. You could easily fall through that. But this is how the Inuit now have to try and get about in this very unsafe way, with water on the surface of the ice sheet, even though you can see it's exactly the same ice sheet in the same position as it was 6 years earlier. This is a 6-year interval between these two pictures. Next slide, please. The Arctic also is warming faster than anywhere else in the world. We don't completely understand why, but the amplification in the Arctic is about 3 or 4 times, so that everywhere in the Arctic, which we already see is melting, is melting faster than you expect because the temperature is rising more rapidly than anywhere else in the world. Next slide. And we can see that as well if we look at a region which we didn't expect to be warming very fast, which is Siberia. And here, the summer months over the last 70 years, we can see that in the last few years, there's been a far more rapid warming in Siberia than in the previous 50 years. Next slide. And the result of that is something which nobody ever expected to see, a brush fire in the Siberian Arctic. This is the Siberian taiga. This is forest. It's forest which is normally covered in snow. It's what you think of as Siberia. You think of this, Anna Karenina stuff, and it's not. Suddenly, spontaneously, the forest is catching fire, and this was a brush fire which started 2 years ago, and it just got bigger and bigger. The reason was the Russians weren't doing anything about putting it out because it's too remote, so it just expanded, and then in the intervening winter, it kept smouldering and erupted again in the following summer, and probably has erupted again this summer. So it's an eternal brush fire, and the area occupied is greater than any other brush fire in the world. So it beats all the Californian brush fires. So here we have a Siberian forest, which you don't expect ever to be warm, being the site of the world's largest brush fire. Next slide. This is a more familiar brush fire in California. I just showed this because I happened to be driving by one day in Pasadena and saw this smoke coming up. I thought this must be a building on fire. But as we approached it, we found actually it was a canyon which was protruding into the city and had caught fire. So this fire lasted about 4 or 5 days. Next slide. And had the normal thing of helicopters trying to put it out. And because it was across the freeway were closed for 4 days, and that was pretty bad for drivers. But this is becoming normal now, and it's normal now for small towns to just catch fire, and we've all seen the terrible events of towns burning down. But this is part of a city. This is Pasadena. It's not a small town. Next slide. Another thing that's interesting, I'm just going through a collection of horrors, is that the area of ice in the Arctic, curiously, is not at the moment decreasing. We know that it's disappearing, but it's disappearing from the bottom up rather from the outside in. So this is the summer ice extent in 2012, in September 2012. This is the summer ice extent in 2020. You can see that the total area of ice is about the same. The area of ice is the coloured bits. But if you look at the thickness scale, we can see that 2012 there were ice that was 2, 3, even 4 meters thick. But in 2020, the ice was only 0.5 meter or 1 meter thick. So it looks as if there's still plenty of ice in the Arctic. The area is the same, but instead of being quite solid and thick ice, it's very, very thin ice. It's really just about to disappear, but hasn't yet disappeared. Next, and this is the ice as it used to be. The really thick ice that called multi-year ice that was several years old, if you tried to walk on it or walk to the North Pole, you'd have a lot of trouble. But you wouldn't have any trouble now because the ice is only about a foot or two thick. Next slide. The other thing that's changed is that we can't do things on the ice anymore. Back in 2007, when I did this experiment, this would be the typical way scientists would work in the winter, would be they'd fly out a load of huts, prefabricated wooden huts, set them up on the ice, set them up with a diesel generator and labs and workshops, and make a little village on the ice that would last 2 or 3 months, and we'd do lots of work. The trouble was that we were using aircraft to take all this stuff out, and you can't do that anymore because the ice is breaking up all through the year. Even in winter, there's big cracks everywhere. You wouldn't be able to have a runway, and so we can't work anymore from ice stations. Next slide. So you have to do this. You get an ice strengthened ship. This is a French ship. Freeze it in, and you sit on the ship, and maybe you venture out to a tent to do some measurements. But on the whole, you're stuck on a ship that's beset in the ice. This is the only way to survive if you're trying to do ice work. Next slide. Of course, the best way to measure ice thickness is with a submarine. And this has been something I've done for many years. I think I've done 6 trips to the North Pole in submarines. And you use an echo sounder looking upwards from the submarine at the bottom of the ice. This tells you how thick it is. And this is one of the things that show how rapidly it's thinning. So to get up in, this is an example of them showing you how you can, what it looks like to resurfacing in ice. In other words, they put you ashore, you photograph the submarine rising, and then they come back and pick you up. And the person on the left that you can't see is Dougie Allen, who was Attenborough's photographer. Next slide. This is how you live if you're a scientist on a submarine. That is, they don't take great care of you. They make you sleep in torpedo stowage racks rather than in a nice cabin, because they don't have any nice cabins. And this is my colleague Nick, who's now in Norway. Next slide. And this is the data you get. You see that the ice, at least in the past, would have these very deep ridges where the pressure of the wind acting on the ice has piled it up into ridges which can be 40 and 50 meters deep. This is what the bottom topography used to look like, but now it doesn't because there's scarcely any ridges left. It's just the thin ice. Next slide. And this is how the change happened during the 70s and 80s. The blue is average ice thickness in the Arctic, in different parts of the Arctic, measured with British and American submarines. And the green is what that was like in the 1990s. Blue is what it was like in the 1950s. So we see already about half the ice has gone, and this was only in the 1990s. A lot more has gone since then. Next slide. So what are the other consequences? Because the biggest problem is that the changes that are happening are affecting, even when it's just the increases CO2, it's causing climate changes everywhere. So some of the ones I'm going to talk about is the Greenland ice cap is melting because of warming of the surrounding seas, where they're losing their ice. The biggest threat we have at the moment is the danger of a huge methane release from the Arctic seabed. This is something we really have to worry about. Then there's a problem of slowing of the jet stream, which is what's causing many of our climate and weather events, which tell problems for crops, and acidification of the oceans. So I'll look at these. Let's start. Next slide, please. With the simplest one, which is that the oceans are getting more acidic because we got more CO2 in the atmosphere that dissolves in the ocean to produce carbonic acid, and the ocean acidity goes up. That is, its pH goes down. If you've done chemistry at school, so the acidity of the oceans is going up, and that means that things that dissolve in acid, i.e., shells of marine creatures, will dissolve more in an acidic ocean. And we're finding that the shells of both of tiny creatures like foraminifera, which are only that big, and bigger creatures, bigger marine creatures that have shells, are just melting away. They're disappearing. And so those shells can no longer do their job, which used to be when the creature dies, the shell sinks to the seabed and is lost, and that's a way of getting rid of some carbon dioxide. But now they don't. They dissolve on the way down, and we don't get the carbon dioxide removal. Next slide. Then this is the methane threat, which is something I've been working on. And the weird thing about it is you can see that this is depth contours, and most of the central part of the Arctic is very deep water, but around the edges you have very, very shallow water. These continental shelves are only 50 or 100 meters deep. Next slide. And on the seabed there is a big layer of sediment, which is actually methane, which has reacted with water to form this kind of weird material called methane hydrates. It's a way that methane is held in the sediments. And this is some that was dredged up. And this is really called ice that burns, because this stuff, if you set light to it, it will burn. It looks like ice, but it's not ice. Next slide. Here's some methane coming up through the seabed in the Arctic and burning. Next slide. And the Russians have been working in this area and measuring huge plumes with echo sounders, where you see here all of these are rising plumes of methane gas coming up to the atmosphere from the seabed, which is only 50 meters down. Next slide. And this shows some photos taken from an autonomous vehicle showing the bubbles rising to the seabed, getting flattened against the remaining ice on the surface. Next slide. And here they are just on the way up. So we're getting these huge and increasing amounts of methane bubbles rising up to the surface from the seabed in these shallow parts of the Arctic Ocean. Next slide. And this is causing one of the causes of the big increase in methane content of the atmosphere that we're seeing. For instance, we thought that the methane in the atmosphere had reached a steady level. That's the blue here. But then in the after 2010, suddenly the level started to rise. And this is a measuring station in the Arctic, in Alert. And you can see that not only has the methane content started to rise, that's the red, but there's all these little blobs around, which was called by a Danish scientist dragon's breath. It looks as if maybe it's some careless measurements, but actually all those blobs are real, and they're little packets of methane gas that have been emitted from the water or from the ocean or from the land are passing across the measuring device, and because it's methane and therefore it burns, but he calls it dragon's breath. But it's just a sign that methane is getting out of control. Next slide. Next slide, please. Yeah, okay, so this is the methane level in the atmosphere, the way in which next one, the way in which, having reached a peak, it then took off again and is taking off like mad now, and is trying to catch up on carbon dioxide as the chief source of greenhouse gas. Next slide. The other thing related to disappearance of ice is the disappearance of permafrost. Permafrost is frozen ground where you have permanently frozen ground that's a sort of a mixture of ice and frozen dirt and frozen vegetation. And it occupies a huge area. This is permafrost in the Northern Hemisphere. And it's you can build on it, and in fact the Russians do build houses on it, and it was reckoned to be a permanently safe, solid material, and then it started to thaw. So here we have permafrost as it was. Next slide. Next slide, please. But then when you measure the temperature of that permafrost, it's rising, and this is a measuring site. The place that I know pretty well is called Dead Horse, not a very inspiring place. It's listed in the atlas, in atlases of having a population of one, and the one person is the person who works at the airport and arranges flights for oil company people to get out. But they do the measurements here, and we can see how, like every other spot where you do any measurements on permafrost, it's warming up. Next slide. This is when that permafrost sort of reaches a certain level, it just collapses. And this is a huge area in the north of Alaska where the permafrost has collapsed, and the dirt and muck and everything has flowed out to sea. Next slide. This is a cliff that's left behind. So you can see it's ice, but it's not ice. It's not pure ice. It's ice mixed in with vegetation. Next slide. So here's what happens as it thaws. It's a vicious circle. The atmospheric warming at the top of here causes permafrost to thaw. When it thaws, you then have this gunk, this vegetation, rotting vegetation, which stopped rotting because it froze. It's a bit like if you go to if you haven't cleaned out your freezer for a long while and you go and look at what's in there, you find this gunk, this terrible stuff that's sort of a messy green rotting stuff. That's what thawing permafrost is like. But as it thaws and it decomposes, that releases more carbon dioxide. So decaying permafrost is a big source of carbon dioxide and of methane. Next slide. And this is some of the consequences of building on permafrost, which everybody thought was perfectly safe. But as the permafrost thaws, you start to find your buildings collapsing. Next slide. And sometimes they completely collapse. So that's an extra factor. Decaying permafrost over half of the Asian and North American continent is going to continually increase the amount of methane and in the atmosphere. It's a big source. And so, of course, is this seabed in the Arctic Ocean. So we're in for really increasing greenhouse gases unless we can do something serious about it. And the other big source of methane, of course, are livestock. And this is a to scale model in which David Attenborough will feel very sad because all the wild animals in the world occupy this tiny corner. That's the total biomass of wild animals. Bigger is biomass of humans, but biggest of all are cows. We are controlled by cows, and cows have got 2 stomachs and they emit a lot of methane from burping. And one of the biggest sources of methane in the world are cows. People don't like to think about it, but it is the case that when we eat meat, especially when we eat beef, we are contributing to global warming by a huge amount. It's something like 40%. Next slide. So these are various estimates of impact of food, that the global emissions come from our animal products, not from plants, because plants are benign and you just grow food you have large areas to grow food in, but you don't have with animals. You're limited because they need more space, and you're limited by the fact that they're emitting methane. So it's a bigger impact than people think. Next slide, please. So a few more horrible things. The fact that sea level is rising. Now, that's because mainly at the moment, it's because the Greenland ice sheet, which is 3,000 or 4,000 meters thick, is melting. It's melting because the surrounding water is now water and not sea ice anymore, and it's causing the temperature on the top of the Greenland ice sheet to rise. Next slide. And the estimates of how much sea level rise that's going to cause are constantly themselves increasing. And that's because IPCC, the government panel, Intergovernmental Panel on Climate Change, is an extremely complacent organisation which tries to minimise what's going to happen. And they've been forced to make steadily increasing estimates of what global sea level is going to do. Next slide. And we can see the rate doubling. These are observations here, and we can see that the rise of sea level in the world has risen from 2.2 millimeters a year to 3 and now to 4.6. In other words, we already doubled the rate of increase of global sea level in the last since the year 2000. Next slide. When we look at the Greenland ice sheet, we find it's melting in a very obvious way. And I was lucky enough to be standing on it on the day when the biggest amount of loss happened ever in a single day. It was 12.5 billion tons melted off the top of the Greenland ice sheet on August the 1st of 2019. The reason it melted was, of course, the air temperature was 21 degrees, which you don't normally get the temperature ever rising above freezing point on the Greenland ice sheet because you're 3,000 or 4,000 meters up. But in this case, it was shirt sleeve temperatures and the ice was melting like mad. Next slide. This shows one of the bad effects of that is that the ice melts, but it leaves the dirt behind. There's dust, there's soot from brush fires, there's dust from dust storms. The whole surface of the Greenland ice sheet is very dirty. It's like a car that hasn't been cleaned for several thousand years. But when the ice melts, it gurgles away and melts down towards the sea, but leaves the dirt behind. And this is called black ice. The trouble with black ice is that it's black, and that means it's absorbing more solar radiation. So it's speeding up the loss of the Greenland ice sheet. Is just being speeded up by the fact that the Greenland ice sheet is now covered with dirt, black ice. This is one of the things I'm studying at the moment. Next slide, please. This shows the edge of the glacier. That was the top of the ice sheet. This is the edge, and we can see again how what you think of as pure ice is completely hidden by dirt, and this dirt is giving it a coating which makes it dark and makes it melt quicker. And here you see it melting, forming an actual kind of torrent of meltwater, which goes straight into the sea, of course. In this case, we were a group from a company that does electric car racing and does scientific work at the same time. So we had a group of rally drivers collecting ice samples for us. Next slide, please. So I thought you might like to see some of the heroes of electric car racing. Jensen Button, who used to be a GT driver, now does electric car racing because it's more ecological, and he goes around also helping us to collect ice samples. Next slide. But of course, the rising sea levels are just rising inexorably, and we don't have any way of dealing with it. It's not, you can get rid of carbon dioxide from the atmosphere by various heroic methods, but when the ice has melted and it's in the ocean, there's not much you can do except endure the fact that we're going to have a flooded world. Next slide. Well, I guess I'm getting a bit short of time, so I'll miss out these ones, but they're showing the very wide range of sources that there are for methane. Carbon dioxide is easy. We burn anything, we burn oil, we burn coal, we burn anything. It produces carbon dioxide, makes the climate warmer. But methane, there's various sources. There's this seabed source, there's the decaying permafrost, there's, as you can see here, there's termites. Termite nests involve production of methane, wetlands. Next slide, please. And then that's natural, and then there's us, which is producing land rubbish, huge rubbish tips emit methane. Cows, as I said, emit methane. Rice cultivation emits methane because of the wet rice stalks and burning biomass. So it looks a pretty hopeless task to try and find ways to reduce seriously the methane emissions. And in fact, I think it is a pretty hopeless task. Next slide. That's methane. The final thing, horror, I want to talk about is the jet stream. And that this is, again, a product of the Arctic heating up. When the Arctic heats up faster than the rest of the world, then the air above the Arctic gets warmer than relatively speaking, than the air at lower latitudes. So we have a polar air mass sitting over the top of the North Pole, and then we have warmer air at lower latitudes. Now that difference between the polar air and the warmer air is itself decreasing because the polar air is warming up faster than the rest of the planet. So that decreasing temperature difference causes a slowing down of the jet stream. The jet stream is that very powerful wind that blows around the world, and it's caused by this temperature difference between polar air and tropical air. With that temperature difference going down, the jet stream slows down. So instead of being a single strong wind, it's now broken up into these kind of meanders. Next slide. And so there we see what used to happen on the left, and what happens now is that the cold air and from the polar air mass and the warm air from the tropics interact, and you get these this weak jet stream, which is meandering around in all directions like a river that's slowly flowing. Next slide. Now, the trouble with that you can get really extreme events happening. That if we go back 2 slides, I'm afraid. Yeah, that one. You can see that used to be a straight line wind, but now you can see that a wind coming down from the north, polar air, can get right down into the United States. And here, hot air coming south can get right up into the Canadian prairies. You're getting cold air or hot air going to places where they don't belong. And that's what we've been noticing in the last few years, these extreme events of hot or cold events. Okay, so when we look at where that happens, it's happening at that boundary, the jet stream boundary. And unfortunately, that coincides with the place where we grow most of our crops. If you look at the brown here, this is where the world's crops are grown, and they're grown in North America, in Europe, in the Ukraine. This is our big places where we grow our food, but they're also the latitudes where they're most affected by these weather events. And next slide. And the trouble is that there's 2 things going on at the same time. The climate is getting warmer, and that's reducing the yields of all of these standard crops. You can see the yields as the temperature goes to more than 2 degrees above the pre-industrial, the yields of crops go down. So that's messing us up, messing the world up. But on top of that, you've got these fluctuations due to extreme events. Next slide, please. So when you get those 2 things happening together, there's a real disruption to crops. And that then affects the world. One example of this is the United Nations has a World Food Index. What's the average price of food? Of course, this is today in Britain, of course, this is relevant. But in 2000, they started this World Food Index at 100. It's the average price of food throughout the world. And within 8 years, it had gone up by more than 100%, gone up from 100 to 220. Then it went down for a while. Now it's gone up again, and it's gone up even more. And I hate to think what it is now. But each time it rises to a peak, all the poor countries of the world, where they can't afford to grow food or buy food, become really distressed. So these are countries that had extreme distress during the first big peak, and even more distress the second peak. And you can see these are countries where there's been wars and insurrections, and nobody can live at peace in a country where you can't afford to buy food. But this is what's happened because of a mixture of global warming in general and these extreme events due to the Arctic air interacting with the air at low latitudes. Next slide, please. Okay, so what can we do? Finally, very finally, what can we do? We know that the rate of population increase is greatest in, these are various estimates of population increase during by 2100, where the one that is most, the region that's most rapid is here, Africa. Africa's due to quadruple its population by the end of the century, while other regions are increasing by maybe 30%. So there'll be enormous difficulty in feeding the people of Africa. In fact, there already is, but this will be far, far worse. Next slide. We're not doing anything about this, by the way. as I've shown that CO2 is rising all the time, it's rising most rapidly in China and India. Europe has got some control, but China and India things are just going wild. Next slide. And we have to do something about it, but we don't know what to do. At the moment, we're trying to replace fossil fuels with renewable energy, but we're not doing a good job at all. Well, we are in Orkney, but not many other places. If you look at the sources of the global use of energy, the big ones are still oil, coal, and natural gas. The little ones at on the bottom right side here are the things we want to be using: nuclear, hydro, and renewable energy. But instead, we're still obsessed with using massive quantities of fossil fuels. We haven't managed to cure ourselves of that at all in any way. So that's disastrous. What can we do? Next slide, yeah. The trouble is, the Intergovernmental Panel on Climate Change says the way to do it, the way to cure ourselves, is to emit less, cut our emissions. But I don't believe that for one moment that will work. The way to save us is to find technical ways of getting rid of carbon dioxide from the atmosphere. If you cut emissions, the best you can do is to have the same amount of carbon dioxide in the atmosphere. And that's no good. You're not going to cool the climate that way. The only way is to get the CO2 level in the atmosphere down. And what some scientists, and including people in my group, are working on is how can we get rid of carbon dioxide from the atmosphere so that the actual level goes down and we can have a climate which is livable. So next slide, please. This is one of the ghastliest pictures I've seen. It's the Intergovernmental Panel on Climate Change rejoicing that with the Paris Climate Agreement, they've beaten climate change. Of course, they hadn't beaten it, and they hadn't even started, but they were congratulating themselves on how wonderful they were. Next slide. Well, at least there's an agreement to reduce emissions, but that, as I said, that's not enough. You have to take CO2 out of the atmosphere. And I'll just show, it's not too late, I'll show the last 2 or 3 slides which show how we're trying to do this. This just shows how we failed. The red is carbon dioxide emissions, and all the markers here are UN conferences where they were supposed to agree to reduce emissions. And you can see the emissions have not been reduced at all. They just keep increasing at an increasing rate. But here's some ways that work, and we haven't tried them properly yet. But the first one is Scottish, so I think it deserves a mention, and that's marine cloud brightening. And this was developed by Stephen Salter at the University of Edinburgh, and I really hope he gets the support he needs to put this into full-scale effect. What it is that you have an unmanned vessel, a sort of drone ship, with pumps inside in which you pump seawater up through these masts, which are called actually Flettner rotors, they're propulsion systems. You pump it up through the mast to a very finely divided nozzle at the top, and it comes out as a kind of a fine spray through this nozzle and goes into the bases of low-lying clouds, that is marine stratus clouds. And when the fine enough material goes into a cloud like that, it brightens up the cloud. And this has been shown to work. You instead of a dismal grey cloud, you get a bright cloud. And the bright cloud reflects more radiation back into space. So it's actually allowing the Earth to get rid of more radiation. So Salter's calculated that about 50 of these would make a 2-degree difference to our planet. So it's not an enormously expensive, it's not a huge, it's quite huge, but not gigantically huge method. And if we can just start doing it, we can start to actually reduce the temperature of the planet. So I don't know why it's not being done, but it's not. Nobody's giving Salter the money he needs. Other methods do exist, and this is called biochar. And what it is you take agricultural waste and you pyrolyze it. That is, you burn it in a digester without any oxygen present. So it turns into something that looks like charcoal, but this also takes away carbon dioxide. So if you tow these things around fields and you can digest agricultural waste and get biochar, which is a useful material. Next slide. This is a material this is a Californian case where they're doing it with pistachio kernels. Next slide. Okay, but the really best way is take carbon dioxide out of the atmosphere by turning it into something else, or simply by passing it through something which simply takes away the CO2. And that was invented a long time ago for submarines. But the one that works really well at the moment is a company called Blue Planet, where it's converted into limestone. You take the carbon dioxide out of the atmosphere, you react it with a carbonate, and you get limestone, and the limestone can then be used for construction, for making cement, so you can get negative carbon cement. Next slide. And this shows nodules of this carbon, this limestone that's been produced by this method. Next slide. And here it is embedded in cement to produce a concrete which is more limestone than cement, and so it's carbon negative concrete, where instead of being carbon positive, and this has been, as a demonstration project, this has been used to re-roof one of the terminals in San Francisco Airport. So it's a wonderful method. It produces carbon negative concrete, which is, and concrete's normally the most wasteful material in the world for carbon. Next slide. And it's also being done by companies where instead of making limestone, you just pump the carbon dioxide into caverns. And there's a company that pumps it into caverns in Iceland, where you've got lots of hollow mountains, volcanic mountains, and there's a company called Climeworks which does that. And these are various other methods where you run the carbon dioxide through these cleaning methods that take it out of the atmosphere, and you convert it into something else. That's what needs to be done, but on a gigantic scale, and it's not being done because of this obsession with carbon emission reduction. We're not doing the carbon removal, which we should be doing. Next slide. Well, the person who's trying to keep everybody on track here is Greta Thunberg, and of course, when seeing the mess which we've made of climate and how we're failing to do what needs to be done to save ourselves, we're dependent instead on the next generation. So people like Greta and her generation, they are the ones who will have to pick up where we've failed, and so we hope that they can and help save us. So that's it, and I like to, of course, advertise my book, available from Penguin, and that next one is the final one, and just for the sake of the Science Festival, there is a film, a very nice full-length feature film called Ice on Fire, all about climate change and what you can do about it, made by Leonardo DiCaprio, and it's got lots of stuff filmed in Orkney. It's filmed at EMAC, the testing range in Orkney, and you've got Neil Commode is one of the mega stars there, and they show how it's done and how wave energy is converted into electricity. So I think that's a nice film, got lots of Orkney pictures in it. So that's about it for climate and what we can do about it, if anything.
Peter, thank you very much. That was a most impactful presentation. Yes, we're running over, but I've got time. There's a lot of questions coming, and I'm going to have to apologise to some of the people who've submitted questions because we're just not going to be able to tackle them all. There's common themes are coming in, Peter. You've touched on the increase in the albedo of the clouds and things with the cloud generator, basically. There's comments coming in. Somebody says perhaps there is the root cause of all the gross is it gross overpopulation? Is that the real root cause? And perhaps our species, nature's got a mechanism for culling us to control that.
Well, I say unfortunately yes, but it's not so much population as what we do. If the Earth could withstand a high population, if it wasn't for the fact that population is busy driving around in SUVs and making stupid things in factories that they don't need. It's the way people live, the type of society we've got that's wrong. We could probably tolerate a population that's maybe as great as we have now if we lived sensibly and sanely, but we're not. It's the way we live as well as our numbers that's important.
Yeah, I've got to get to the $64,000 question. Is that it? Have we had it? Are we out of control?
Well, at the moment we are out of control, but we can save ourselves. I mean, I always run out of time when I start to talk about carbon dioxide removal, but I think that's the solution. That you can technically, without it's not rocket science, remove carbon dioxide from the atmosphere. And it was invented, the scrubbing of carbon dioxide was invented in 1920 for use in submarines to restore make them breathable. But you can do it. If you take it out the air and you put it somewhere, like under the sea, in a cave, or you turn it into something useful, like limestone was chosen because there's 40 billion tons of carbon dioxide that we put in the atmosphere every year, disastrous. And if we want to get rid of that and use it for something useful, we need some material where you need 40 billion tons of it per year. And the only thing really that fits that is cement, concrete. That uses 40 billion tons a year. So if we can make carbon negative cement and concrete, or in this case limestone, we can not only reduce the CO2 in the atmosphere, but do it in a useful way. So there's nothing to stop us from actually saving ourselves by carbon dioxide removal. But when you look at the people who have developed methods that work, you find there's no money. Like Stephen Salter's case, one of the, he's a great scientist. He's the kind of Barnes Wallis of this time, a brilliant inventor, and he developed this system for marine cloud brightening, but people are messing around with it, doing little tests. Nobody's doing a full-blown deployment of marine cloud brightening on the planet. Ditto with any of these other methods of CO2 removal. Everybody says, oh yes, it's wonderful, we must do this, we ought to do it, but nobody does it. And I think we're out of control because we're not taking the problem seriously enough. I mean, look at our pathetic government we've just formed. Nobody in that government has said anything at all about climate change. They're not even aware that it's going on. It's not important to them. And it's the same with other pathetic governments, and it's not just Britain, but it's this fact that people think we don't have to really do anything for 20 or 30 years. But in fact, scientists know that in 20 or 30 years, we'll be dead. I mean, the planet will be uninhabitable. Temperatures will be so high that industry living will kind of stop. You've got to do all this now, and we're not doing it. So many scientists despair of the human race, that we seem to be committing suicide as a species, and we don't need to, because we have got methods of getting out of this, but we're not applying them.
Peter, I'm going to have to bring this to a close, but can I thank you, the audience, both online and in the theatre, the questions, the comments, the concerns that have clearly come through from our Slido and things. Peter, thank you so much for that fascinating and, well, dare I say it, a very concerning talk. It was an eye-opener for me personally. I knew about a fair bit of it, but I needed you to put it all together and hit me with it to have the impact it actually requires. I'm going to suggest this is a must watch for everyone. We need to share the link to the recording of this event far and wide.
Yes, Peter, I'd be happy to see that. Yeah,
we will do that. Thank you so much for that, Peter.
Okay, pleasure.
And now to the festival. For those of you online, can you please complete a feedback form? The link should be in the YouTube chat or Slido now. And those of you watching the live stream at the cinema, could you please use the link in Slido or fill in a paper copy and leave it with the door team on your way out. It helps us shape next year's festival to make it relevant and an improved experience for yourselves. I'd also like to draw your attention to the Aviation Festival, which follows on immediately after this one, starting tomorrow, the 8th of September. There hopefully is a link appearing to it in the YouTube chat and Slido now, but we'll also post it on our social media so that you can access it. Once again, Peter, thanks so much. And can I support the technical support team in the background, who we had a fair bit of work to do to get this to you. They did a splendid job and deserve every congratulation that we can give them. Thank you much for everyone. For now, until the next time, goodbye and thank you.
Goodbye. See you next year, I hope.